Welcome to this new video where we will see a new coding problem, the find pair that sums up to k problem. This problem says, given an array of integers r and an integer k, create a boolean function that checks if there exists two elements in r such that we get k when we add them together. I hope that you try to solve the problem, so let's start. First of all, we have to understand the problem. We have to exactly know what does our function have to do. Here we want to find two elements such that we get k when we add them together. So as soon as we find those two elements, we return true. And the first solution that may come in your mind is the brute force solution, where we check all the possible pairs until we find one that sums up to k. For example, if we have this array of 5 elements, we check the pair of elements at indexes 0, 1, then 0, 2, then 0, 3, then 0, 4. Then I becomes 1 and we repeat. We check 1, 2, then 1, 3, then 1, 4. And we continue like this for all possible pairs, until we find a pair where r of I plus r of g is equal to k. After checking all pairs, if no one sums up to k, we return false. And the Python code of this solution is, we define our function findPair that takes as parameters the array of integers r and the integer k, then we start looping. Here to check all possible pairs we need two for loops. The outer loop where I starts at 0 and stops at r length, and the inner loop where g starts at I plus 1 and stops at r length. G starts at I plus 1 because if it starts at 0, we will traverse pairs that we already traversed, so it's useless. And inside the inner loop, if r of I plus r of g is equal to k, we return true, because we found a pair that sums up to k. After the loop, if the function didn't return true yet, it means that we didn't find what we're searching for, so we return false. This solution works, but it's not the best one, because even if it has a constant space complexity, it also has a time complexity of O of n squared, because of the two for loops, which is not the best one for this problem, so let's search for another solution. Now let's suppose that we have this array that is sorted, and that we are searching for a pair that sums up to 10. Let's take for example the first and last element, 3 and 9. When we add them together, we get 12, which is greater than 10. Now we have two choices to check another pair. We can either increment the left one to check this pair, or decrement the right one to check this pair. But what do we choose? To know which move we have to do, we will use the characteristics of a sorted array, because we said that the array is sorted. In a sorted array, each element is greater than or equal to the precedent one, and each element is smaller than or equal to the next one. It means that now that we have this pair of elements that sums up to 12 and we have to decide which move to do, we know that if we increment the left one it will be useless, because 3 plus 9 is already greater than 10, and incrementing the left one will make it go to an element that is greater than or equal, so the pair sum will increase or remains the same, and in both cases it can't go down to 10. Which is the case here. If we increment the left one, the new pair sums up to 14, which is greater. So we deduce that moving the left one will increase the pair sum or make it remain the same. And the opposite for the right one, we said that each element is smaller than or equal to the next element. So moving the right one will make it point to a number that is smaller than or equal. So our pair sum will decrease or remain the same. And knowing these two information, what we can do is that we sort the array first, because the input array is not necessarily sorted. Then we use the two pointers technique, one that starts at the first index and one at the last index. Then if we add r of left with r of right and we get k, it's perfect. This is what we want, so we return true. Else if we add r of left with r of right and we get a sum that is smaller than k, we have to make it bigger, so we increment the left pointer in the hope of increasing the sum to make it reach k. Else, it means that our sum is bigger than k, so we decrement the right pointer, in the hope of decreasing the sum to make it reach k. And all that while left pointer is still before right pointer, because if we don't stop after it, we will just traverse the same pairs, so it's useless. After the loop, if the function didn't return true yet, it means that we traversed all the necessary pairs and we didn't find one that sums up to k. We return false. To better visualize this solution, let's apply it to this example. We have this array R and K being equal to 14, so we are searching for a pair that sums up to 14. First, we sort the array. Then we put our 2 pointers, one on the first element and one on the last element. Now we have R of left plus R of right is equal to 1 plus 12, which is 13, which is smaller than 14, so we increment left pointer to get a bigger pair sum. Now we have 3 plus 12, it's 15. Now it's the opposite, it's bigger than 14, so we decrement the right pointer to get a smaller pair sum. Now we have 3 plus 9, it's 12, which is smaller than 14. We increment the left pointer. And now we have 5 plus 9, which is equal to 14. So we found a pair that sums up to k, we return true. The Python code of this solution is to first define our function findPair, then we sort R. Then we create and initialize our 2 pointers to the first and last index respectively. After it, we have the loop. While left is smaller than right, if R of left plus R of right is equal to k, we return true because we found the pair. Else if their sum is smaller than k, we increment left. Else, we decrement right. After the loop, we return false because we didn't find a pair. The time complexity of this solution is O of n log n, because we have sorting the array that costs n log n and traversing the necessary pairs that costs n, and n log n plus n gives O of n log n. For the space complexity, if you are allowed to modify the input, because don't forget that you have to sort it, then it's constant. Else if you're not allowed to modify it, it means that you have to create a copy of it to avoid modifying the original one. So we get a space complexity of O of n. Even if this solution is better than the first one we've seen, we still can do better. Let's find a solution that runs on O of n time complexity. Now what if, for example, we would be able to check if a certain value exists in the array without having to traverse it again? For example, we have this array and we are searching for a pair that sums up to 12. What we want to do is that we traverse the array, then when we arrive to 10 here we can say, wait, to reach 12 I need to be with the value 2, and I already found it when traversing the array, so we can form a pair that sums up to k. It means that we want to store the values that we already visited, until we find the other element of the pair. And the best way to perform this task is to use a hash table. It can have another name depending on the language, but the concept remains the same. The hash table is a powerful tool when solving coding problems, because it has an O of 1 lookup in average, so we can get the value of a certain key in O of 1, and it has O of 1 insertion in average, so we can insert an element in O of 1. So what we can do is that while traversing the array, we store the actual element in our hash table that contains visited values, then as soon as we find that we already visited k minus the actual element, we return true. Why k minus the actual element? Because it's the value that we want to add to the actual element to get k. For example, with this array, we start with an empty hash table, because we didn't visit any element yet. And we start. Does 12 minus 8, which is 4, exist in the hash table? No, we store 8 and we continue. Does 12 minus 2 exist in the hash table? No, we store 2 and we continue. Does 12 minus 9, which is 3, exist in the hash table? No, we store 9 and we continue. Does 12 minus 5, which is 7, exist in the hash table? No, we store 5 and we continue. Does 12 minus 10, which is 2, exist in the hash table? Yes, we already seen it, so we return true, because we have a pair of elements that sums up to k. The Python code of this solution is to first define the function findPair, then we create an empty dictionary to store the visited values, and we start iterating over the elements. For each element in R, we check if k minus element exists in the dictionary, so we write if visited.get k minus element, and if it's a truthy value, it means that k minus element exists, so we return true. Else, we just put our element in the dictionary and we continue. After the loop, if the function didn't return true yet, it means that we didn't find any pair that sums up to k, so we return false. And this solution runs on O of n time complexity, because we said that lookup and insertion are constant in average in hash table, and we are traversing the n elements of R, So we get O of n, where n is the number of elements of R. Same thing for the space complexity, it's O of n because we are using additional space for a hash table that can contain n elements in the worst case. I hope that you understood these solutions and you can find their code in other programming languages below, so check the code and see you in the next problem.